We live in a world of just instant answers, right? We expect to find anything we want, anywhere, in literally a fraction of a second. But how does that actually work? Today, we're going to pull back the curtain on the invisible logic that powers our digital world, search algorithms. Let's dive right in. I mean, really think about that for a second. You type blue running shoes into some huge online store, and before you can even blink, boom, there are your results. It honestly feels like magic, but it's not. It's a really carefully solved problem. And how it's solved is the difference between an amazing shopping experience and a super frustrating wait. At the very heart of this problem is this classic showdown. Do you use the simplest, most obvious method you can think of? Or do you go for a clever, way more efficient one that, maybe requires a little more setup? This battle between just being simple and being efficient is a core idea in all of computer science. And look, this isn't some abstract theoretical thing. You rely on search algorithms every single day. Finding a song on your playlist, looking up a contact in your phone, even just searching for a file on your own computer. It's all powered by the exact same principles we're about to break down. So let's kick things off with the most straightforward approach, the one we'd all probably invent ourselves if we had to. It's called linear search. The name really says it all, doesn't it? You've got a list of items, and you're looking for one specific thing. Well, linear search just starts at the very beginning and checks every single item, one by one, in a straight line until it either finds what it's looking for or it runs out of items. Simple, right? The process is just so intuitive. You look at item number 1. Is this it? Nope. Okay, on to item number 2. Is this it? Still no. And you just keep going, right down the line. It's basically brute force, but hey, it gets the job done. Oh, this is the perfect way to think about it. Imagine a teacher has a roll call list, but the names are all jumbled up. They're not in alphabetical order. To find one student, what do they have to do? They have no choice but to call out every single name from the very top until someone finally says, "Here." That, right there, is the essence of linear search. Now, in computer science, we have a way to measure this. It's called time complexity. And for linear search, we say it's O of n. That fancy n just stands for the number of items in your list. All it means is that the time it takes to search grows in a straight line with the size of the list. So if you double the items, you could potentially double your search time. But what if there was a smarter way? A strategy that didn't involve checking literally everything. Let's bring in our second contender, an incredibly clever approach called binary search. Okay, now this is absolutely crucial. The big requirement for this method is that the list must be sorted. Binary search only works if your data is already in order, kind of like a dictionary or an old school phone book. But if it is, oh man, this algorithm becomes unbelievably powerful. And this is why it's so powerful. Instead of just checking one little item at a time, binary search's very first step gets rid of half of all the possibilities. Gone. Every single guess you make cuts the problem in half. It's a massive, massive leap in efficiency. Think of it like you're playing a higher or lower guessing game. You jump right to the middle of your sorted list. Is the word you're looking for alphabetically before or after this middle word? If it's before, you can completely ignore the entire second half of the list. Just throw it away. Then you just repeat that process, having your problem again and again and again. The time complexity here is called O of log n. And what that means is, well, it's truly amazing. Even if your list doubles in size, say from 1 million to 2 million items, a binary search only needs about one extra step to find what it's looking for. The growth in search time is just tiny compared to the explosion in the amount of data. It's insane. So we have this gut feeling that one is way, way faster than the other. But how do we actually prove that? Let's look at the language computer scientists use to make it official. Yeah, it's not enough to just say, well, it feels faster. In programming and engineering, you need a standard, official way to measure and compare performance. And it has to be independent of how fast your computer is or what programming language you're using. And that standard is called Big O notation. You can think of it as the universal language for talking about efficiency. Big O doesn't care about the exact time in seconds or milliseconds. All it cares about is how the number of steps grows as your list gets bigger and bigger and bigger. It is all about scalability. To really truly feel the difference, let's stop talking in the abstract and use a huge number. okay? Imagine we are searching for one specific item in a list that contains 1 million things. With our good old linear search, if we're super unlucky and our item is the very last one, or maybe it's not even in the list at all, we have to do 1 million checks. We have to look at every single item. All right, now for binary search on that exact same list. How many checks in the worst case scenario? About 20. No, that is not a typo. 1 million versus 20. By just repeatedly cutting the problem in half, you get to the answer with an astonishingly small number of steps. And this chart just says it all. I mean, it's hard to even show these two things on the same graph. The bar for linear search would be a skyscraper, and the bar for binary search is basically a welcome mat on the ground. This visual just makes the power of a better algorithm completely undeniable. So, does this mean you should always use binary search? Well, not necessarily. The final and maybe most important piece of the puzzle is knowing when to use which tool. And this is probably the key takeaway for anyone interested in programming or just problem solving in general. The goal isn't to just memorize the quote-unquote best solution. It's to understand the trade-offs so you can pick the most effective tool for your specific situation. And this table really brings us to that crucial trade-off. Look, if your list is small or if it's completely unsorted, the simplicity of linear search is honestly perfect. It's easy and it just works. But for a huge, sorted dataset where speed is absolutely critical, binary search is the undisputed champion, even with that upfront work of having to sort the data. And that's really the core idea here. This isn't just about code. It's a whole way of thinking. It's about knowing when a simple, straightforward approach is good enough and when a divide and conquer strategy can make a seemingly impossible task totally manageable. So the question I want to leave you with is this. Where could this kind of thinking save you time in the real world? Thanks for joining this explainer.